Hey guys, welcome back. We now understand the core elements and concepts in Kafka. It is now time to talk about reliability. Kafka is a distributed environment with many nodes working together, and this means there are potential chances for failures. Let's now talk about fault tolerance. In this lesson, we're going to talk about failures related to producers and consumers and how fault tolerance is achieved with producers and consumers. In the next lesson, we'll talk about fault tolerance with Kafka brokers. Let's first start with a producer failure. The job of a producer in Kafka is to produce messages and put them in a topic in Kafka. That is it. The producer does not care about who is consuming the message, how many consumers consume the message, and it does not even care whether any messages it produced was ever consumed or not. The producer's job is done as soon as the message is pushed to the topic. This makes dealing with producers' failure very easy. Also, producers are efficient. Instead of pushing one message at a time, producers push messages to Kafka in batches, either at a specific interval, say every 10 milliseconds, or once the message size reaches a specific limit, say 64 KB. This way, we have few I/O operations hitting the Kafka cluster. In our case, the Twitter service is our producer, publishing the tweets to our Kafka cluster. Since the Twitter service is pushing messages to Kafka, it has to be written with Kafka API. We will see how to write a producer and consumer in Java in the upcoming lessons. Let's say our Twitter producer fails and went down. In this case, our Kafka cluster and our consumers are not affected because the producer is not tightly coupled to Kafka cluster or the consumers. The producer does not even need to be on the same network as the Kafka cluster. The only downside of producer failure is that we won't get any more tweets or messages from the producer until the issue on the producer's side is fixed and the producer is brought back up. But the good news is our Kafka cluster and our consumers are not affected and they are up. And as soon as the producer is back up and starts sending messages, we will be able to process them. Now let's talk about consumer failure. We have three consumers in our consumer group. And let's say consumer 1 went down. From our illustration, we can see that consumer 1 is assigned to process messages from partition 2 and 5. So when consumer 1 goes down, Kafka will notice that and will trigger a rebalancing operation and will distribute partition 2 and 5 between consumer 2 and 3. We can assume partition 2 will be assigned to consumer 2 and partition 5 will be assigned to consumer 3. But remember, a partition can only be assigned to one consumer and not to multiple consumers. But one consumer can be assigned to more than one partition. Now let me ask you an interview question. Ready? Let's say consumer 1 went down and partition 2 is now assigned to consumer 2. Now will consumer 2 process partition 2 from where consumer 1 left off, or will consumer 2 process partition 2 from the beginning? What do you think? If you were to guess, you would say consumer 2 will process partition 2 from where consumer 1 left off, because it sounds logical, right? And that is correct. Now, as an interviewer, I would ask a follow-up question. How does consumer 2 know from where to start? If you answer Kafka server or Kafka brokers would keep track of the location from where consumers should start reading, you would be dead wrong, because that is against the design of Kafka. Remember, in the first lesson in this chapter, we said Kafka design principle is keep the broker dumb and consumer smart. Kafka broker does not keep track of the messages that are consumed by consumers. It is the consumer's responsibility. The answer to the question is offsets. To understand offset, let's understand how messages are stored in partitions first. Kafka essentially maintains a log-like structure for each partition. Let's look at an illustration. Here, we are looking at 5 partitions. We have tweets as messages in each partition. T1 represents tweet 1, T8 represents tweet number 8, etc. As messages come in into the partition, they are appended to the end of the log. End of the log meaning right here. For partition 1, 0 is the beginning and 7 is the end right now. So next message coming in for partition 1 will end up in offset 8. Can you notice the order of messages in the partition? You can see the tweets are not continuous inside a partition, but tweets are stored as it came in. That is, inside the partition, the tweets are ordered. This means we don't have global ordering of messages. All we have is messages ordered inside a partition. But Kafka guarantees messages inside the partition are ordered as they came in. The numbering in each partition denoting the position of the message in the partition is called the offset. Offset is like index inside each partition. Consumers will start reading from offset 0 of a partition and increments the offset as it reads through the partition. Message from the producer ends up in the end of the log. Consumers does not have to match the pace of the producers. It can consume in its own pace. As consumer consumes the messages, the consumer increments the offset. Now let's go back to our scenario. Consumer 1 in our illustration is assigned to process partition 2 and 5. Let's assume consumer 1 has processed message at offset 2 in partition 2 and offset 4 in partition 5. All of a sudden, consumer 1 went down. As soon as consumer 1 went down, Kafka will trigger a rebalance operation because no consumer is currently processing partition 2 and 5. So both partition 2 and 5 will be independently assigned to the alive consumers. Let's assume consumer 2 is assigned to process partition 2 in addition to partition 4, which is already processing. Now consumer 2 needs the last offset that consumer 1 processed. Again, it is consumer's responsibility to keep track of what it consumes. Consumers in Kafka will record the latest offset it processed for each of the partition it is responsible for into an internal topic in Kafka. So latest offsets for all the partitions in the topic by consumer group is recorded by the consumers. So when a consumer is assigned to a partition, it will fetch the latest offset for that partition from the internal topic and start processing messages after the offset. We will be using Kafka API to write consumers, and you don't have to worry about the offsets at all in your code, but it helps you understand how it all works behind the scenes. Prior to Kafka version 0.8.1.1, the offset information is recorded in Zookeeper. When you have a lot of topics and partitions, recording offset in Zookeeper does not easily scale. And hence, in later versions of Kafka, consumers record the offset information in Kafka's internal topic. Let's say in our Twitter use case, each of our consumers process about 4,000 tweets a second. Do you think it will be an overhead to record the offset in the internal topic 4,000 times a second? It is absolutely an overhead, right? So how do we handle recording the offset information as efficient as possible? There are a few options provided by Kafka. The first option is we can enable auto commit for our consumer, which will enable the consumer to record the offset every 5 seconds by default. This is the easiest option, but we might end up with data duplication. Let me show you how. Let's say consumer 1 is configured to perform auto commit every 5 seconds and is now processing partition 2 and recorded offset 2 in its last commit. Now 3 seconds later, consumer 1 went down. But just before it went down, consumer 1 processed message in offset 8. Since consumer 1 went down 3 seconds later than the most recent commit, the last offset recorded was 2. But in reality, consumer 1 last processed message in offset 8. This would mean when a new consumer start processing partition 2 after the consumer 1 failure, it would start from offset 3 instead of offset 9, thereby duplicating the processing for messages from offset 3 to 8. This is not ideal. Luckily, there is another option. Just few minutes ago, we said producers for efficiency push messages to Kafka in batches. Similarly, consumers for efficiency process messages in batches. And at the end of every batch, we can perform a synchronous commit to record the offset. Meaning, we'll process a batch of messages, trigger a commit, and wait for the successful execution of the commit, that is, recording the offset before processing the next set of messages. Later in the chapter, we will write Java code to consume live RSVP stream from meetup.com, and we'll see how we can perform a synchronous commit in action. Sync commit looks like a good option, but in a high-speed messaging environment, it could slow down the consumption because we're essentially waiting for the commit to complete before processing the next batch of messages. There is one more option where you can asynchronously commit and thereby proceed with consumption without waiting for the commit to complete. There is a trade-off though. Since you're not waiting for a commit completion to process the next batch, the recorded offset could go stale if a commit operation failed. So asynchronous commit is not as reliable as a synchronous commit. The commit option you choose greatly depend on the use case of your application. If you care less about duplication of data and the velocity of data coming in is light, you can go with auto commit option and commit every 5 seconds. If you care a lot about keeping data unique, then synchronous commit could be the only option. Before we wrap up the consumer fault tolerance, I just wanted to stress one more thing. Here in our illustration, we can see 3 consumers from a consumer group. You can totally have another consumer group with its own set of consumer processing the same topic and partitions in the topic. Look at this illustration. Here we have another consumer group with just one consumer processing messages from the topic. Since we have only one consumer, the same consumer is assigned to process messages from all partitions. The speed at which the consumer in consumer group 2 process messages from the partitions is independent of the consumers in consumer group 1. And consumer 1 and consumer group 2 will record the offset information per partition independently of the consumers in consumer group 1. So anytime you have a consumer processing a partition, the offset information is recorded separately. Because at a later point, if you decide to add consumers to consumer group 2, Kafka will trigger rebalancing and partitions could get reassigned to another consumer. And the new consumers will need the offset information of the partitions to continue processing without duplicating the consumption. All right, so far we looked at how fault tolerance is handled both at the producers and at the consumers. We looked at offsets and how we can control recording the offsets in consumers. Next, you guessed it right, we'll see how fault tolerance is achieved at the broker level. See you in the next lesson.